Flipped Classroom video for Maths A2 Unit 3, Connected Rates of Change. In the video on the chain rule, it was called the function of a function rule, and it was called the chain rule. And it's not obvious why it's called the chain rule. We can see from y equals f of g of x that it is a function of a function. And this form here, g dash x times f dash g of x, again is involving a function of a function, as in f dash of g of x. So this form reflects the name function of a function, but there is an equivalent form which reflects the name of the chain rule. And that is that if we define y equals f of u and u equals g of x, so that would give y equals f of g of x, which is what we started with at the top, then we get dy by dx equals dy by du times du by dx. And so it's starting to form a chain of differentiated functions. And you can see this equivalence in the video M2.3.6b, number 4, proof of the chain product and quotient rules, where it's used in one of the proofs there, the proof of the chain rule. Okay, now why is this interesting? Why is this useful? Well, if nothing else, it means we can use this to look at connected rates of change. So examples of this are, if we would say increasing the volume of a sphere by pumping air into it, and we knew the rate that air was going into it, how would the radius change? It's not at all obvious. Another example, if we were pouring liquid into a container, and that could be a sort of bowl shape or it could be a cube, but depending on the shape of the container, the depth of the liquid will change in different ways, and that means we've got connected rates of change going on. That may or may not make a lot of sense to you, but having a look at an example hopefully will. So the example we're going to look at first is that we have a sphere, and there is a handy picture of a sphere. The radius of this sphere is increasing at a constant rate of 10 centimeters per second. And we are asked to find the rate at which the volume of the sphere is increasing when its radius is 80 centimeters. So we have to start by sort of setting up the problem. So we're going to say that r is the radius, very imaginatively, and v is the volume of the sphere. And what do we know so far? Well, we know that dr by dt is 10. And notice that rate always means per unit of time. So the rate of change of the radius with respect to time, which is what dr by dt means, is given to us as 10. And we don't worry about the units at the moment, we'll stick them in at the end. Okay, now what we've been asked to find out is what rate is the volume of the sphere increasing at. So we need dv by dt. Now using the chain rule, we can say that dv by dt is equal to dv by dr times dr by dt. And again, remember that dv by dt means it's per unit of time. So this is the rate. So that's what we were asked to find the rate at which the volume of the sphere is increasing. Now we know what dr by dt is, but we don't yet know what dv by dr is. But we do have a formula that connects the volume of the sphere with the radius, and that is v equals 4/3 pi r cubed. Now we can differentiate that with respect to r, which would give us, well, if we differentiate r cubed, that gives us 3r squared. The 3 we get cancels with the 3 on the bottom of the fraction in the formula for v, so that leaves us with dv by dr equals 4 pi r squared. Pi is just a constant, of course. So now we can say that dv by dt is equal to 4 pi r squared times 10. Now we want dv by dt when r is equal to 80. So the 4 times 10 in the line above has become 40. There's our pi. And because r is equal to 80, the r squared becomes 80 squared. We pop that into a calculator, or do it in our head if we're very good at arithmetic, and we end up with 8.04 times 10 to the power of 5 centimetres cubed per second. Notice, as I mentioned earlier, we stick the units in at the end. So that's one example of how we can use connected rates of change. And now we're going to look at a slightly different idea, and that's using the reciprocal of a derivative. Okay, so we've already seen that dy by dx is the same as dy by du times du by dx, and this means that if we replace x by y, we'd have dy by dy is the same as dy by du times du by dy, and that means that 1 is equal to dy by du times du by dy, and that means that dy by du is equal to 1 over du by dy. Now, that's a very useful result. It is important to remember that dy by dx is a symbol, and we can't just apply algebraic rules to it, or to the components of it, and it does sort of look like we are doing that, but that's useful because these formulae do work a bit like ordinary algebra, which can help in remembering them, but we must remember all the time that when we say dy by du equals 1 over du by dy, we're not just dividing the top and bottom by dy. It isn't quite as simple as that, but it does work that way, so as it says, you know, that helps us remember it. Okay, why does this matter? Well, the consequence is that if we needed in some sort of connected rates of change situation dx by dA, but we've been given a as a function of x, so if we have a as a function of x, we can differentiate that and get dA by dx, and then we can use 1 over dA by dx equals dx by dA. Now again, that's very sort of wordy, and the best way of making sense of it is to look at an example. So the example is that we have a cube, and the volume of this cube is increasing at the rate of 0.2 meters cubed per second, and we want to know at what rate the length of the side of the cube's increasing when the side length is 3 meters. So at some point the cube will become 3 meters on the side length. We want to know at that point what is its rate of increase. What do we know? We know that dv by dt is equal to 0.2. The rate of change of volume is equal to 0.2 meters cubed per second. So what do we want? Well, we want dx by dt. We have dv by dt, and using the chain rule we know that if we times that by dx by dv, then that will give us our dx by dt. So we know what v is. V is equal to x cubed, and that means we can work out dv by dx, which is 3x squared. But we don't want dv by dx, we want dx by dv. So we recognise that dx by dv is equal to 1 over dv by dx, so that's going to be 1 over 3x squared. So now our dx by dt becomes, well, we know that dx by dv is 1 over 3x squared, and we know that dv by dt is 0.2, so those multiplied gives us our dx by dt, and we want to know what this value is when x is equal to 3 for the side length, so we pop that in and we get that dx by dt when x is equal to 3 is equal to 3 times 3 squared times the 0.2, and that gives us 0.0074 meters per second.